Okay, now we're going to begin a new section, which is chapter 5 on your book. And now we are going to talk about centroids and center of gravity. So this is because we're introducing the concept of distributed forces. If you remember, some problems had objects where with any shape, could be a bucket, could be a plate, and it has a mass, and that will make it heavy. Therefore, there's a weight, and that force is equal to the mass times the gravity. So the mass is given, the gravity we know is fixed in here on Earth, and the force can be found. So the important thing about centroid is that we conceptualize the force applied at the center or at the centroid. So in a rectangular shape, it's very easy because it will be at the center. Um, let's say a square is the center in the x and the y direction. This is completely centered. But we're gonna learn that for other shapes, it's not so easy. If it's an irregular shape, you have to use the integral to compute the area and then get the x and y coordinates to tell you where is the centroid. But yeah, some common shapes are known. So like the circle is the origin, rectangular shape, we'll see that it's pretty easy to find. It's not um, closer to the top angle, is closer to the base. And we'll see how to find that. We'll also find the centroid of a parabola in case some shapes need to have um, additions or subtraction of parabolas to get the shape. And this parabola can have any function. So it could be steep or could be pretty flat. Okay, so in the applications, as we said, is that sometimes we have to find the distributed load or we have to apply the load somewhere. So that point, the centroid, is very useful to apply a single force that corresponds to the whole distributed force. So in this example, we have a roof that has a distributed force because of the snow. It's like so. Okay, so these forces like this are all over the roof. But if we want to find a single force, we can conceptualize as a very large force that is a summation of all the forces applied somewhere in the centroid of the roof. Okay, so the concept is basically that if we have a shape that is irregular, irregular meaning that is not a square, a circle, a triangle, or any of the regular shapes that we know, a cylinder is just a arbitrary shape. We can find the center or the centroid by knowing the coordinates x and y and doing a summation of the delta w. Okay, so the delta w is a vector that is perpendicular to the geometry applied at a point G. And with the coordinates x and y, we can find the centroid with respect to x and centroid with respect to y. So ideally, the only thing you have to do is compute the integral of the x variable. So as you move across the x-axis and multiply by the deltas of the points. So it's easier to see in an example. Oh, but before we do the example, let's talk about what happens if the geometry is not a solid. What happens if it's a rope or a string? The centroid might not be on the actual mass or the volume. It might be outside. And it's the same concept. You compute it based on an integral of all the segments of x and y across the geometry. All right, so this is a good example. So the centroid of an area is the same as having computed all the delta areas at every x and y. Or let me say that again. If you notice that on the left-hand side, we have every x and y multiplying the delta area. So we're sweeping in x and y direction, and every segment of area is being computed. So we're integrating the area. But the same thing is if we know the centroid and we multiply by the x distance from the axis to the point and the y distance from the axis to the point, that area could be found like that as well. So those two things are similar, or the same actually, they're equal. That concept is called the first moment with respect to the axis. Okay, so the first moment of area is the name, the first moment of area. And they're very useful because they're the points where we applied forces. And the same thing for a string or for a rope. The centroid could be outside of the actual geometry. But if you have a rope on the floor, for instance, if you try to lift the rope, the actual load or the single force could be conceptualized as a force applied over here outside of the rope, meaning that if you try to lift it, this part will be the heaviest if you think about it like that. The only difference between a volume and a string, or an area and a string, is in an area we have a differentiation with respect to the area, or x and y, versus in a string we have a differentiation with respect to the line or the length. So the deltas are delta lengths. Okay, but that's just the concept. So a lot of times we don't really go into a very complicated example to get this concept. But it's important to understand that we can find the centroid by integration. So this is a good example, or a good way to see the concept. If we have our axis x and y, and we have a defined function, so this is a defined function, and we are given the point which will have coordinates x and y in 2 dimensions. This is R2. The centroid, which has in 2 dimensions, will be in x and y. The centroid is the multiplication of the x distance from the origin to the point where the centroid is located at, which is this equation right here. I didn't mean to go out of the slide. Okay, let's try that again. Yes. All right, so that equation right there is telling us that this distance, if it's known, times the delta area, and the delta area is, as we saw before, are the little segments of area throughout our domain. This delta area has units of length squared, and this x of distance has units of length. All right, so you can see how this is length squared, this is length. The same for y. This computation will give you the first moment of area in x, and this computation will give you the first moment of area in y. In 2 dimensions, the units are length, cubic length, or meters or inches, but it will be length cubic, in 3 dimensions. The first moment of area will give you 4 dimensions. It will be length to the fourth, so meter to the fourth power or inches to the fourth power, etc. But the equation is quite simple. It's the differentiation of area, or in the macro scale would be the area times the distance from the centroid, and the y scale in the y-axis will be the area times the distance in y. And the distance in y will be this distance. All right, so that is for irregular geometries. It could be complicated if the function is not very straightforward. If the function is mathematically complicated, then integrating could be hard. But the concept is very straightforward. It's just a multiplication of the distance times its differential in area. Another different thing will be how easy it would be to integrate this function, and that's a completely different thing. So this class is not about calculus so much, it's about the forces and the statics and the equilibrium. So we would not have to do complicated functions at all. And this is another example where you can actually have a set of coordinates in transfer to polar coordinates or keep it in rectangular coordinates, where in rectangular coordinates you start from here, but you can do a transformation and then do the angle, which we know how to do the angle, cosine, and do the centroid in distances. So sometimes mapping to a different coordinate system will actually be pretty useful. All right, so this is a good example, and we have a parabola. The example is telling us to compare or find the centroid of the body. So we have a rectangular coordinate system in x and y. We know that that is R2, it's 2 dimensions, and the function, the area, is enclosed by this distance a and the distance b in y, and the function is a constant k, and of course a parabola. So we can actually find k because we know the distance a and b. A and b would be any numbers, it could be 10 and 5, etc. So to find the constant k, we simply plug the numbers that we have. So when y equals to b, we have b equals k x squared, but the boundary of x, this range, is a squared. So pretty easy, we already know that k is equal to whatever b is divided by a squared. Hence, this function, this specific function, is b over a squared times x squared. So it would be easier if we do integration varying in x, but since it's an area, we can find the area with this integration. But to find the distance from the centroid in y, they would the variation in y would have to be solving the equation for x. So what I mean is that if you have this equation, what you have to do is have x by itself, and that will take a squared times y divided by b is equal to x squared, or square root of this is x, which means that a square root of y divided by a square root of b is equal to x. Yeah, like so. Okay, so obviously this one will be much easier to differentiate than this one. Okay, because this is x squared and this is square root of y, but both are doable. These are constants, so we don't have to worry. These are numbers. All right. So the area, as we were saying, the area, we will need the area, we will need that piece of information to find our centroid. The area is the integral of all the elements in X and all the elements in Y. Okay, so area is composed by elements in X and the elements in Y. That's basically the definition of area, right? If you have a square, it will be the distance in horizontal units versus the distance in the vertical units. Okay, so what we have to do is basically integrate the y variation with respect to x, or the x variation with respect to y. But I was saying it's easier to integrate this formula or this equation right here. And that's where basically the example is telling us to do. So the integration of this thing is basically the integral of b divided by a squared, which is a number. If they give us numbers, that will be just a single number. This is 10 and 3 or whatever. We compute this, and x squared dx, right? So this is constant x squared dx, and integrating this, you know how to integrate this part. Is b a squared and is x cubic divided by 3, and this is evaluated in x from 0 to a. Okay, so that is basically b a squared. We just need to evaluate this part at a cubic divided by 3 minus, when it's 0, so this whole thing is 0. So that is equal to a times b divided by 3. Okay, so that is a long way, but now this is the good thing about using AB in general terms. Any single time you have this shape, which is a parabola, the centroid, the centroid of the parabola is at 1/3 of the limits, A and B. So if they give you a parabola where this is 5 and this is 2, the centroid will be at 1/3 of 10. All right, so it's pretty simple. Now, sample problem, what is this? It's a similar thing. What is the difference here? Let's perform a single integration where, okay, so now this is just to find, I apologize, this is not to find the center, this is to find the area. So the area of this parabola is at 1/3 of a times b. But if we want to find the centroid, this is here. Yeah, the centroid is the x direction. Of course, the centroid, this is basically telling us the centroid has to be a distance in x and has to be at a distance in y. All right, let's try this again. So we already have this part done, and where we're saying that this is actually an x, and y is y distance, which is y over 2, therefore the integral is b over a squared times y, which is y distance over 2 times x, which is the x squared. Okay, but x squared, and then y, it will be dx. So this is equal to b, a, then x. So this would be integral of y over 2 times y dx. So this is equal to integral of 1 half of b a squared x squared times b a squared x squared dx, which this is equal to 1 half b squared a to the 4th and x to the 4th dx. Okay, this is equal to 1 half b squared a to the 4th. The integral, no, it's not integral anymore, is we can actually integrate it and get x5 over 5 from 0 to a, because we're in terms of x, and this is equal to 1 half b squared a to the 4th of a to the 5th over 5 minus 0. So this is equal to 1 half b squared a to the 4th times a to the 5th over 5 equals to 1 over 10 a b squared. Okay. Alright, that's how it looks like. Okay, so this is the point that I want to get at. So if they give you, this is a table that is very useful. A lot of the geometries that we encounter have this have some type of rectangular shape or half circle or full circle or parabola or triangle. So in please go over this table and understand and have it handy. So the area of the triangle is the base. I don't know if maybe this is too small, so let me go ahead and type it out. Is base times height divided by 2. And the y coordinate, the centroid, is located at 1/3 of the height. Okay, for a circle, the area is pi r diameter squared, or pi r squared divided by 4 if it's a single, if it's a quarter of a circle, or divided by 2 if it's a half circle. So if it's a full circle, if it's a full circle, is pi, the area is pi r squared. Okay, if it's a half circle, it's obviously that divided by 2. If it's a quarter circle, it's pi r squared divided by 4. Okay, so if it's a quarter circle, the centroid is located in x at 4 times the radius divided by 3 pi and it's actually the same place in y. So the moment of a quarter circle would be x times the area. So this number times that number. So go ahead and go through the circle. We already did the parabola. The area is a times h divided by 3, and the distances in x are 3 times a divided by 4 and 3 times h divided by 10. So this is what I was saying. The distance in y is 3h divided by 10. So when you multiply these two things, this is what I'm going to find out if there's a typo or not. In y is going to be y times the area. So it's 3h divided by 10 times ah divided by 3. Yeah, so ah divided by 10.